Hello, welcome back to Cardinal Science for part 2 of Introduction to Organic Chemistry. Following on from part 1, we'll be looking at points 4.5 and 4.6 today. Understand how to write the possible structural and displayed formulae of an organic molecule given its molecular formula, and 4.6, understand how to classify reactions of organic compounds as substitution, addition, and combustion. Before we get started addressing these specification points, it's important to do a little bit of background on alkanes and alkenes because we'll be using those as examples, but these do come up later in the specification. So just to remind ourselves, so alkanes have the general formula of CnH2n plus 2. So you have twice as many hydrogens plus 2 for every carbon that you have, and it's made of only single bonds. Typical structural formula of an alkane consists of CH3 groups at either end of the molecule with some number of CH2 groups in the middle. And I represent this with a little X there. So if we have a 3-carbon chain, then it will look like what I've just drawn, but without the brackets and the X. If it was a 4-carbon chain, we'd have 2 CH2 groups in the middle. If it was a 5-carbon chain, there'd be 3 CH2 groups in the middle. Every time we would have a CH3 group on either end and some number of CH2 groups between them. Typical displayed formula would have exactly the same pattern, except of course we draw the actual bonds. So the one I've just drawn, for example, would look a bit like this. We could kind of bracket that and put an X. And likewise, we have our CH3 at the end. So we could have any number of CH2 groups in the middle there, and it would still be an alkane. CH3 groups on either end, CH2 groups in the middle. Alkenes are slightly different. Our general formula is CnH2n. Now the structural formula and the displayed formula is a bit more tricky. So the structural formula will represent the fact that there are double bonds in there. Now each carbon can only have 4 bonds in total, which means the number of hydrogens will change depending on where the double bond is. So a structural formula might look like CH2, CH2 if you have a 2-carbon alkene, or you might have something like CH2, CH, CH2 if you have a 3-carbon alkene. So 4.5 we briefly covered in the last video actually. What we need to be able to do is convert molecular formula into structural formula. So we need to remember that a structural formula shows which atoms are bonded without showing the bonds themselves. So if I have a molecular formula of, say, methane, CH4, in this case actually the structural formula is the same because of course we've only got 1 carbon. But if we have something like, let's say, propane, C3H8, the molecular formula that I've just written doesn't tell you which carbons those hydrogens are bonded to and in what order. So what we do instead is we show how many hydrogens there are bonded to each of the carbons. And in this case, we have 3 bonded to the first carbon, 2 bonded to the second carbon, and then 3 bonded to the last carbon. And as you can see, we've still got 3 carbons and we've still got 8 hydrogens. Let's just do one more for practice. Say we had butane, C4H10. We do the same thing. So we're going to have 3 hydrogens on the first, 2 on the second, 2 on the third, and 3 on the fourth. Remember, with alkanes, that's anything that ends with an ane, we'll have this kind of structure. We'll have CH3s on either end, and all the carbons in the middle will have CH2 groups attached. So again, we can see we have 4 carbons on the bottom here, and we have 10 hydrogens. So very similar to what we've just done, but this time we'll be converting to displayed formulae. So same as before, we have methane, we have propane, and we have butane. So we want to convert each of those to its displayed formula showing all the bonds. Okay, so in the first one, we just have 1 carbon and it's bonded with single bonds to 4 hydrogens. And there's our methane displayed formula. Our propane, so we draw our 3 carbons, and then we need to put our hydrogens around it, ensuring that each carbon only has 4 bonds in total. So there's one on the left, we'll have 1 there, and there, and there, CH3, and see it's got 4 because it's got 1 single bond to the other carbon. This carbon in the middle, we only have 2 hydrogens because it's got 2 single bonds to the adjacent carbons. And the last carbon will have 3 hydrogens because it's only bonded to one other carbon. And there's our displayed formula for propane. Now for butane, it's very similar indeed. It will look just like propane, but with one more CH2 group in the middle. So we'll have 1, 2, 3, 4, and we'll have hydrogens around them. Notice the ones in the middle only have CH2 groups, and the ones on the end will have CH3 groups. If we count them up, you'll see that we have 10 hydrogens and 4 carbons. When we refer to substitution in organic chemistry, what we really mean is swapping. So substitution reactions occur when atoms on an organic molecule are replaced or swapped by other atoms during a reaction. So, for example, when alkanes react with halogens. So in A level you actually learn the mechanism for this reaction, but let me just show you what this might look like. So an alkane here, so we've got ethane. Okay, and we're going to react that with a halogen. So any halogen would do, let's say chlorine. Now what we get in this reaction is a substitution reaction. And so we substitute one of the hydrogens that are bonded to those carbons with one of the chlorines. So we produce something that looks like this. So there's a chlorine there, and all of these hydrogens remain unchanged. So what we've done is substituted this hydrogen for one of those chlorines. And what we produce as well, the hydrogen that comes off bonds to the chlorine that's remaining and forms HCl. So you can see we've substituted one of the hydrogens for a chlorine there, and it's therefore a substitution reaction. Let's do another one for some practice. Say again we have ethane, and we're going to react that this time with fluorine. So pause the video and draw the displayed formula of the product after this substitution reaction. Okay, let's have a look then. So just as before, we're going to replace one of those hydrogens with a fluorine. It doesn't actually matter which one, so it's fine wherever you put it. So I'm going to put mine up here. I've replaced that hydrogen with one of the fluorines, and of course we need to make sure we can balance this. So the hydrogen that's come off bonds with the remaining fluorine, forming hydrogen fluoride. Unsurprisingly, addition reactions occur when atoms are added to molecules during a chemical reaction. So we'll do an example. These tend to occur when alkenes react with halogens. So let's do ethene, so 2 carbons double bonded and both bonding to 2 hydrogens each. And react one of those with chlorine, for example, and what we get is an addition reaction which forms something that looks like this. So the double bond breaks and you add on both of those chlorines onto the molecule. So you can see that we have no other products. We had 2 reactants and now we only have 1 product. We've added those 2 together. We've added atoms onto the ethene. It's an addition reaction. So for practice, let's do one more. We'll make it slightly more challenging. So let's say we have propene. So we have 2 carbons double bonded together with our hydrogens. This carbon will only have 1 hydrogen. This carbon will have 3. Okay, so we're going to react that with bromine, Br2. So we're going to do an addition reaction here. So pause the video, see if you can add on those 2 bromine atoms correctly onto that molecule. Okay, here we go. So just again, we break the double bond, and the carbons that are deficient in hydrogens essentially will be given the bromines. So our bromine will go here, and our bromine will go here. And so we've essentially formed an alkane, and we actually call these alkanes that have halogens added to them haloalkanes. Finally, we have combustion reactions. So combustion is when something is burned in oxygen. Okay, it's a reaction between a substance and oxygen. Now, in combustion reactions with hydrocarbons, we always get the same products, regardless of the hydrocarbon that we use. So, for example, we might show ourselves having methane reacting with oxygen, and it always produces carbon dioxide and water. The only difference is when you balance these equations, you'll have different numbers in them. Okay, for example, you might have C2H4 reacting with oxygen, and again we would produce carbon dioxide and water. Okay, but of course in this case we need to balance it, putting a 2 in front of there and a 2 in front of there, and then we would have 6 oxygens on the right, so we need a 3 in front of the O2 there. But any reaction where hydrocarbon reacts with oxygen producing carbon dioxide and water will be known as a combustion reaction. Okay, so again we're wondering, how is this content examined? Now some of this is actually applied into later topics like I mentioned earlier. However, it could be examined in its current form. So it might say, show the displayed formula of X. For example, they might say methane, in which case I would write down CH4. Or if they said propane, I would write down CH3, CH2, CH3. If I was looking at number 2, show the structural formula of X, they might say show the structural formula of methane, in which case I would draw my bonds on and make sure that I have enough hydrogens. And likewise for propane, I would draw it including all of my bonds. And so we know the difference between structural formulae and displayed formulae. What type of reaction is this? Or multiple choice question, or they might show you a chemical equation or a structural formula as well built into a chemical equation, and give you some options like substitution, addition, combustion, perhaps oxidation or something like that, and you'd have to pick the correct one. And then you might have to write a balanced symbol equation for the burning of oxygen like I did in the previous slide. Once again, thank you for watching Cardinal Science. This has been part 2 of the Introduction to Organic Chemistry. If you found this useful, please leave a like, perhaps subscribe if you haven't already, or leave a comment below if you have any thoughts or questions. Thank you.